Welcome to the Explainer. Today, we're cracking open the instruction manual for the entire universe. Yeah, you heard that right. We're going to break down the fundamental rules that govern every single piece of matter around us. So, where do we even begin with something that huge? Well, how about with a simple question? So, let's just start with this. Think about it for a sec. The air you're breathing right now, the water in your glass, a super hard diamond on a ring, they all seem completely different, right? But deep down, they're all made from the same fundamental stuff. So what is it that makes them behave so differently? The answer, my friends, is all in the world of chemistry. To get to that answer, we first need to see how chemists think. How do they organize this incredibly complex world? Well, they've got it sorted into three basic categories. And once you get these, everything starts to make a whole lot more sense. First up, we've got elements. These are the ultimate building blocks, the Lego bricks of the universe. They're the purest substances that exist. You can find them all neatly lined up on the periodic table. And the key thing here, you cannot break them down into anything simpler. An oxygen atom is just an oxygen atom. That's it.
Next up, we have compounds. Now, this is where things get really interesting. This is what happens when you take different elements, say hydrogen and oxygen, and you chemically lock them together. The result is a brand new substance, like water, with totally new properties. And I mean chemically locked. It's a super strong bond. You can't just, pick the oxygen out of your water.
And finally, there are mixtures. This is the simplest one. It's when you just jumble different things together, but they're not chemically connected at all. Think about sand and water. You mix them up, but the sand is still sand, the water is still water, and you can easily separate them again with something like a filter. No big deal. So, you see, it all boils down to one simple question. Are the atoms chemically glued together, or are they just hanging out in the same room? That chemical glue, that bond, creates something entirely new, like water. Without it, you just have a mixture where everything keeps its own identity. Okay, so that word bond is clearly the key to everything. But what is a bond, really? To understand that, we have to zoom in. I mean, way in, and look at the tiny little particle that starts it all, the atom. All right, I want you to picture a tiny solar system. Right at the center, you've got this dense core called the nucleus, and inside that are protons and neutrons. Then, whizzing around that core, kind of like planets, are these super light electrons flying around in these distinct layers we call shells. Now, these three particles each have their own little personality. Protons have a positive charge, electrons have a negative charge, and neutrons, they're neutral. They don't have a charge. But look at their mass. Protons and neutrons are the heavyweights here. An electron is so light, its mass is practically zero in comparison. And trust me, that little detail is going to become very important. Okay, the single most important number for any atom is its atomic number. It's just a count of how many protons are in its nucleus. That's it. This number is like an atom's fingerprint. It's what makes carbon-carbon and oxygen-oxygen. If you change the number of protons, you've literally changed the element into something else entirely. The other key number to know is the mass number. This is simply the total count of the heavy particles, the protons and the neutrons all bundled together in the nucleus. And since the electrons weigh next to nothing, this number gives us a really good idea of the total mass of the whole atom. Here is a fantastic little tip to keep those two numbers straight in your head. Just remember this: mass equals massive. The mass number is always going to be the bigger, more massive number that you see for an element on the periodic table. Simple as that. So, with just these two numbers, we can become atomic detectives. It's actually really easy. The number of protons, that's just the atomic number. In a neutral atom, one with no overall charge, the number of electrons always matches the protons to keep things balanced. And to find the neutrons, you just subtract the atomic number from the mass number. It's a simple little formula that unlocks the recipe for every single atom in the universe. So we've decoded the atom's internal structure. We know what's inside. But here's the thing. Atoms are social creatures. They rarely stay alone. Now we're going to see how the way their electrons are arranged actually drives them to connect with each other, creating those chemical bonds that hold our entire world together. So why do atoms even bother interacting? Well, you could say the entire game of chemistry boils down to this one simple rule. Atoms crave stability. And they're most stable, or happy, when their outermost electron shell is completely full.
So they will give away, take, or even share electrons with other atoms just to get that stable, full outer shell.
One way they do this is called ionic bonding. Think of it like a transaction, usually between a metal and a nonmetal. The metal atom is like, here, take my outer electrons. I don't need them, and it becomes a positive ion. The nonmetal atom gobbles them up and becomes a negative ion. And what do opposites do? They attract. That electrical attraction is the bond. But atoms don't always give and take. Sometimes, especially when you have two nonmetals, they form a partnership. In a covalent bond, atoms actually share electrons. It's like they're saying, hey, if we both share, we can both pretend we have a full outer shell. This sharing creates these really stable little units that we call molecules. And then you've got metals. They have their own special trick. In metallic bonding, all the metal atoms basically throw their outer electrons into one big communal pool. This creates what we call a sea of electrons that can just flow freely among all the positive metal ions. And it's this sea of shared electrons that holds the whole metal structure together so tightly. Okay, so we've got these different types of bonds: ionic, covalent, metallic. But why does it matter? Who cares? Well, you should, because the type of bond determines the entire macroscopic structure of a substance. And that structure, in turn, dictates every single property we can see and touch in the real world, from how hard something is to whether it can conduct electricity. And there is no better example of this on planet Earth than diamond and graphite. Think about this. Both of them are made of pure carbon atoms. That's it. Nothing else. But they couldn't possibly be more different. And the entire reason why comes down to one thing: how those carbon atoms are bonded to each other. Just look at this comparison. It's absolutely wild. Diamond is the hardest natural substance we know, and it's a terrible electrical conductor. Graphite, on the other hand, is so soft and slippery we use it in pencils, and it's a great electrical conductor. How can the exact same element have such completely opposite properties? Okay, here's the secret for diamond. Every single carbon atom is locked into place by 4 incredibly strong covalent bonds to its neighbors. This creates this perfect, rigid, three-dimensional lattice. All of the electrons are trapped inside these bonds, which means there are none free to move around and carry an electrical current. It's a perfect, unbreakable cage. But graphite, it's a totally different story. In graphite, each carbon atom only bonds to 3 others. This forms these flat, hexagonal sheets, like chicken wire. These sheets are then stacked on top of each other, but the forces holding the sheets together are really weak, so they can easily slide past one another. That's what makes it soft. And that one spare electron from each atom is free to zip around between the layers, which is why it can conduct electricity. And this just leaves us with this final, fascinating thought. The exact same fundamental roles, the same ingredient, carbon, can give us both the soft lead in pencil and the hardest diamond on Earth. It just goes to show you that by understanding these building blocks, we don't just get to explain the world as it is, we gain the power to design the amazing materials of the future.